viewers, I am Thirumalesh. In this video, I am going to discuss about how to calculate transfer function of a system from differential equation and difference equation. So this is the generalized expression of transfer function of a system in Laplace domain. Let's see the derivation behind it. Let this linear differential equation describes a system. So applying Laplace differentiation property to the above equation, we get a0 into y of s plus a1s into y of s plus a2 s square y of s so on equal to b0 x of s plus b1s x of s and so on. So factoring out y of s and x of s, h of s is given by y of s by x of s, that is equal to b0 plus b1s plus b2s square plus so on, but divided by a0 plus a1s plus a2s square and so on. So let's solve an example. So in this example, we are going to write transfer function by simple inspection of coefficients. So the example goes like this. The equation is 2 into d square y by dt square minus 4 dy by dt plus 3y equal to 5 dx by dt minus 2x. So we are going to write the transfer function for the above equation. So the x terms of this equation, or the RHS part of this equation, comes to the numerator part, and the y terms or the LHS part will come to the denominator part. So by simple inspection we can write h of s equal to 5 dx by dt becomes s minus 2x will become 2 divided by 2 into d square y by dt square will become 2s square minus 4 dy by dt becomes 4s, and this 3y will become 3. So this will be the transfer function for this equation. So now we will see how to write transfer function from difference equation. So consider the class of systems whose input and output satisfy a linear constant coefficient difference equation of the form summation k runs from 0 to n ak y of n minus k equal to summation k runs from 0 to m bk x of n minus k. So applying z transform to both sides of the above equation using linearity and time shifting property, we obtain summation k runs from 0 to n ak. This y of n minus k will become z minus k, z power minus k into y of z, that is equal to summation k runs from 0 to m bk. This x of n minus k will become z power minus k into x of z. So mark this as equation 1. As discussed in the previous slides, we can write transfer function as h of z equal to y of z by x of z. So rearranging the terms in equation 1, we obtain the transfer function or the system equation as h of z equal to y of z by x of z, that is equal to summation k runs from 0 to m bk z power minus k divided by summation k runs from 0 to n ak z power minus k. Mark this as equation 2. So let's solve an example regarding this. Suppose the system function of a LTA system is given by h of z equal to 1 plus z inverse whole square divided by 1 minus 1 by 2 z inverse into 1 plus 3 by 4 z inverse. So we need to find the difference equation for this one. So let's express this h of z in the form of equation 2 in this form. And multiply the numerator and denominator factors. We can write the above equation as h of z equal to 1 plus 2 into z inverse plus z power minus 2 divided by 1 plus 1 by 4 z inverse minus 3 by 8 z power minus 2, that is equal to y of z and x of z. So let's cross multiply this equation. On cross multiplying we get 1 plus 1 by 4 z inverse minus 3 by 8 z power minus 2 whole into y of z, that is equal to 1 plus 2 into z power minus 1 plus z power minus 2 into x of z. So applying inverse z transform to the above equation, we get 1 will become y of n, 1 by 4 z inverse will become 1 by 4 y into n minus 1, 3 by 8 z power minus 2 will become 3 by 8 into y into n minus 2, that is equal to, same is the case, 1 will become x of n, 2 z inverse will become 2x into n minus 1 plus z power minus 2 will become x of n minus 2. So this is the difference equation for this above one. So before solving the next problem, let's have a quick look on the topic, region of convergence. So let me tell you what is ROC, or a region of convergence. The region of convergence is a set of points in the complex plane for which the Z transform summation converges. Through ROC, we can say whether a system is causal or not, or stable or not. So let's see the ROC conditions for an LTI system to be causal and stable. So here are some of the conditions. So the first one is ROC is outside the outermost pole. In the transfer function h of z, the order of numerator cannot be greater than the order of denominator. All poles of the transfer function should lie inside the unit circle. So if a system satisfies these three conditions, these three ROC conditions, then it can be classified as causal and stable. So let's solve another problem regarding this concept. So the problem goes like this. We are given with a difference equation of a system, y of n minus y by 2, y of n minus 1 plus y of n minus 2 equal to x of n. So from previous discussions, we can write the system function of the above equation as h of z equal to x of n becomes 1. So the denominator part, the L of h is we showed in denominator part, the y of n will become 1 minus 5 by 2 into y of n minus 1 will become 5 by 2 into z inverse. Y of n minus 2 will become z of minus 2, z power minus 2. So rearranging these terms, we can write h of z equal to 1 divided by 1 minus 1 by 2 z inverse into 1 minus 2 into z inverse. So this is the pole zero plot for the current example. So let's see, there are three possibilities of ROC for this current example. So for this system to become causal, the ROC should lie outside the outermost pole, that is mod z must be greater than 2. So when this condition is applied, the system cannot be stable in this case. For this system to be stable, the ROC should be mod z lies between 1 by 2 and 2. For system to be both causal and stable, all poles must lie inside the unit circle. But if you can see here, one pole lies, that is pole 2 lies outside the unit circle. So the above system cannot be both causal and stable. So let's solve another example. So in this we are given with an input difference equation and output difference equation of an LTI system. So we need to find the system function h of z and the poles, and plot the poles or zeros of h of z and indicate ROC, and also we need to find impulse response h of n of the system for all values of n, and we need to write difference equation that tells about the system, and we need to tell whether the system is stable or causal. So we know that z transform of a power n u of n is z by z minus a, and similarly a power n u of minus n minus 1 is minus of z divided by z minus a. So we're gonna make use of these properties to solve our problem. So input difference equation becomes x of z equal to 1 by 1 minus 1 by 2 z inverse minus z by z minus 2, where mod z lies between 1 by 2 and 2. So and the output difference equation will become, after z transform, y of z equal to 6 divided by 1 minus 1 by 2 z inverse minus 6 by 1 minus 3 by 4 z inverse, where mod z is greater than 3 by 4. So the system function can be written as h of z equal to y of z minus x of z. On solving, we get 1 minus 2 into z inverse divided by 1 minus 3 by 4 z inverse, where mod z is greater than 3 by 4. So here is the pole zero plot for this example. So we need to find in the B part we are given to find the impulse response, which is nothing but h of n, and it can be obtained by performing inverse Z transform on h of z. So we are going to perform inverse Z transform on this h of z. So it will become h of n equal to 3 by 4 whole power n u of n minus 2 into 3 by 4 whole power n minus 1 into u of n minus 1. So we need to calculate difference equation. So h of z, we know h of z equal to y of z by x of z, that is equal to 1 minus 2 into z power minus 1 divided by 1 minus 3 by 4 z power minus 1. So cross multiplying this, we get y of z minus 3 by 4 z inverse y of z, that is equal to x of z minus 2 power z 2 into z power minus 1 into x of z. So applying inverse transform z transform for this equation, we get y of z becomes y of n, 3 by 4 z inverse will become 3 by 4 y of n minus 1, that is equal to x of z becomes x of n minus 2 into z inverse becomes 2 into x of n minus 1. So whether to tell about stability and causal, the system is stable since the ROC is outside outside, that is mod z is equal to 3 by 4, which includes the unit circle. So from part B, where we calculated h of n, it shows that the system is causal. So these are the references. Thanks for watching.